a case where we had like the first Ebola case or the first case of let's see. I will just move it to the side. All right. The first case of COVID, first case of Ebola, we are just looking at one person, right? And we're trying to see what are your symptoms like? What's the age of it? And so, as you can imagine, we don't need a sample size calculation for that kind of scenario. We also don't need sample size calculations for case series. A case series is a study type where we have multiple cases. So again, going back to the Ebola example or the COVID example, we had the first person who was diagnosed, and then we had other cases. Multiple cases make up a series. Like, think of when you watch Netflix. A series is made up of many episodes. So that's the exact same thing, right? You know, a case series is made up of many, many cases put together, and that gives us a more complete picture. So with case series, we start to do quantitative analysis, like percentages, means, descriptive analysis. But again, we don't need sample size calculation for case series because, I mean, we can't determine how many cases are going to have the disease, right? So we take what we get. Cross-sectional studies, ecological studies, and all the ones above may require sample size. But even at that, there is also a distinction between how we calculate sample size for descriptive studies, which will be ecological studies and cross-sectional studies, versus how we calculate sample size for analytic studies. Analytic studies are studies where you have two groups or more being compared. So analytic studies include case control studies, cohort studies, whether they are retrospective or prospective, and randomized trials. Those are all analytic studies or comparative studies, right? And so when we're talking about sample size in the context of analytic studies, we talk about the word called effect size. Effect size is simply saying what is the smallest gap that we expect to see between the treatment group and the control group. So what gap, what difference between those two would we determine as being something that is significant to us? You, the investigator, you're the one who will set that number. Like you say, what do I consider as something that is clinically relevant? Is the gap this small relevant clinically? Or does it have to be this big? Yeah, you determine that. Of course, know that the smaller the gap you want to see, the bigger the sample size. So the smaller the effect size, the bigger the sample size. You can also compare with the analogy of a microscope. The tinier the thing you want to capture in a microscope, right? The bigger the sample size the microscope you require. So this is supposed to be a pop quiz for you. The more powerful a microscope is, the size of things it can detect. Based on what we just said in the previous slide. Is the answer A or is the answer B?
B, bigger.
A.
A.
Okay. We want the answer. People who answered A and B to defend their answers. Why is it B? Let's start with the B.
Hello.
Yes.
Hello. My own answer is B because the more powerful the microscope is, the more bigger you will see the organism or object placed on it. Because normally objects are very tiny, mostly microorganisms. So once you have a very powerful microscope, the more you adjust the size. That's the size. The bigger you see the object.
Okay. Thank you very much for your insight. The answer of the person who answered A. Can you justify your answer?
Yes, I think it's A because for a start, you only need a microscope to look at things that ordinarily cannot be seen by the eye. So if it's smaller, you need a more powerful microscope to be able to see. So I think it's A.
Yeah, you're absolutely right. So if think of something that is big, if it's big already, well, we don't need the microscope, right? Yeah. Imagine let's talk about extreme, like things that are dramatically big. An elephant. Well, you don't need a microscope to look at an elephant because it's big already. But as we start going towards things that are smaller and smaller, think of an anaerobe, even smaller, right? Think of an electron, right? You start needing a more and more powerful and much more bigger microscope, right? So the smaller the effect, so the point we're trying to make is that the smaller the effect size you want to detect, the bigger or more powerful the study you need. So if you want to detect an odds ratio of at least 1.1, and then researcher B wants to detect an odds ratio of at least 1.5. So 1.1 versus 1.5, which one will have a bigger sample size? The study with an effect size of odds ratio 1.1 or the one with odds ratio 1.5? Which one will have a bigger sample size? 1.1. Yeah, 1.1, yeah. So some of these things, the point I'm trying to make here is that you need to understand these things by first principles, such that without even thinking, you can say, oh, no, that we can't afford that kind of study because the sample size for that will be much bigger. So you should be able to just from by reflex know that, yeah, if I have a study that requires this effect size, this will be the impact on sample size without even having to go and calculate anything. You should know those things from first principles, just that, okay, this is the relationship between power and effect size, because yeah, you need that kind of baseline knowledge. We talked about we also talk a lot about certain types of errors, type 1 and type 2 errors. Again, these are some fundamental things that you need to know just reflexly. You should know that, okay, if the sample size is too small, what will be the impact, right? Just from your spinal cord like that, you should know those things. And that helps you to assess study and, and whether or not there's error in them. And she also talk about the kind of error. So there are two types of statistical errors that are relevant in this context, type 1 and type 2, right? And you can remember the type of error with this story of a guy, the boy who cried wolf. So who remembers this story? We've talked about it before. Who can give us a short narrative of a story? Nobody?
Yes, sir. Yes, sir. Can you hear me, sir?
Yeah, we can hear you, yes.
Yes. Okay, the story is that the boy cried wolf, wolf, and when people came around, they didn't see any wolf. So the next time he cried wolf, wolf, and there was actually a wolf, nobody answered him. So
Exactly.
I think that, if I remember very clearly.
That's excellent. So what was the first mistake that happened in this story?
There were so many false positives.
Yeah.
There was wolf when there was no wolf.
Exactly. So we can call that, can we agree that we can summarize that this was a false positive signal?
Yes,
Does that make sense? That was the first mistake that happened in this story. We had a false positive signal. It's like wolf, but there is no wolf, right? So it was a signal, but it was positive, right? So, and that reminds us of what a type 1 error is. It's a false positive, right? And you come out and you say, oh, our study found a positive association between eating chicken and developing cancer. Wow. And like people are like, wow, that's really, really scary. But it is a false positive, right? In reality, that association, in nature, that association does not exist, but you found it in your study. All right. That is a type 1 error. Who knows the most common cause of a type 1 error? What is the most common reason we have type 1 errors, false positives?
Is it large sample size?
Okay, and not necessarily that could contribute, but that's not the most common reason. But that's a great answer.
When you are looking to add, like
Exactly.
you are looking to add.
Exactly. And
You
that is called different terms, right? We call that p-hacking. We call that phishing expeditions, right? We call that multiple comparisons. People just want to publish their papers so desperately. Somehow they've heard somewhere that there's something called p-value of 0.05, right? And somehow your study has to magically be smaller than p less than 0.05. And so they begin this conquest of finding this p-value. and they compare and like, oh, finally, we have found the p-value. That is the most common cause of a type 1 error. Multiple comparisons, or just going on a fishing expedition. So that's one side. And then on the other side, you have a type 2 error, right? Type 2 error is, in this case, there was now a wolf, but we did not detect the signal. It cried wolf, but we refused to listen. So that's a false negative, right? And so what's the most common reason for a false negative result or a type 2 error?
Sample size?
Yes. What about sample size? Too small or too big?
I think too small.
Exactly, too small. Can you have both type 1 and type 2 error coexisting together?
Yes.
Yes or no? It's not a promise, it's not a trick question.
Yes, sir.
What do you think? Can you have it or you can't?
We have two no's.
Okay.
Yes.
Why can't you have them? For those who said no, why do you imagine that you can't have them coexisting together? Because you're saying that it's impossible to have a study where you have a small sample size and multiple comparisons. But is that really true? Okay, well, you can have both of them can exist. You can have both type 1 and type 2 error coexisting in the study, right? Which do you think is more dangerous, type 1 error or type 2 error? Of course, they are both bad, but which do you think is more dangerous? Let's say let's focus in, let's say, in the pharmaceutical space. Let's say a pharmaceutical company is making a drug for a life or death condition, right? Will you rather have a type 1 error or a type 2 error? Because
We have mostly type 1 and type 2.
okay, so you rather this pharmaceutical company comes out and say that this drug protects lives, when in effect, it does not, right? Or will you rather err on the side of caution and say, well, this drug does not work? So will you rather have pharmaceutical companies overpromise and underdeliver, or just underpromise? That's what we're asking in effect. Because you have to understand what these terms mean beyond just saying type 1 and type 2 error. You have to understand what they mean in real life, right? You also have to understand how we prevent them from occurring in real life applications, not just the theory of it, right? So, so in the case of type 2, in the case of pharmaceuticals, right? Will you rather have a type 1 error? Will you rather try to avoid a type 1 error or avoid type 2 error?
Avoid a type 2 error.
Okay.
Type 1
so
error.
type 1, in general, right? Yeah, in general, because remember that the pharmaceutical company is motivated, or any company, right? They are motivated to show results. So if this result doesn't show positive, well, they can go back and try again, right? And then they can continue investigating in more and more studies. That's fine. So in any day and time, I'll always leave with a type, I would rather we avoid a type 1 error, which is that you'd say that, wow, this drug cures everything, right? When in fact it does not. And so, but again, the condition is always, it's a very dynamic and a very contextual condition, right? In some particular cases, in an entirely different case, it might be better to worry about type 2 error than type 1 error, right? So it all depends on context. But the point I'm trying to make here is that you need to understand what these terms mean in practice, not just the theory of it. And you need to be able to evaluate on a case-by-case basis which one you should be more worried about in any situation, because it's not set in stone. In one particular case, you might be type 1 error might be a bigger problem than type 2 error than in other settings. So you shouldn't just have as if it's hardwired that this is just the way these things work. It varies based on context. So you should have that expertise enough to contextualize any particular problem you're in. All right, let's move on. So this is just to correct a misconception here that I also find very prevalent or very widespread. So here, in the very first sentence here, it says a sample that is larger than necessary will be better representative of the population and will hence provide more accurate results. Can someone critique that sentence? For better or for worse? Do you agree or disagree with that statement? Why or why not?
Yeah, I would say, first of all, a sample size needs, like, once you calculate your sample size, you have to work with that at first in order not to waste resources, especially like in a large study where you're trying to investigate a new drug. And also, it's also good to have like a large sample size because of like so many people might drop out from the study eventually.
Okay.
So it has both its pros and cons.
Okay. I have a problem with 2 words there. Can you guess which 2 words I have a problem with?
Larger than necessary.
Okay. Yeah, no. Try again.
More accurate. More accurate.
Accurate. The word accurate.
Yeah.
And what's the second word?
Better representative.
Exactly.
Okay.
So they claim here is made that a large sample size is associated. The more larger the sample size, the more accurate your results, or the more representative your results. That's a central claim being made in that sentence. So the question essentially is does sample size confer accuracy or representativeness to a study? Yes or no?
I think no. I think there are many factors that we consider, from sampling procedure to biases, measurement bias, and other determinants that really determine the accuracy of results. Not really having a big sample. You can have a very big sample, but if you have multiple measurement biases and selection biases, then the results will not be accurate.
Yeah,
I think so.
Spoken like an epidemiologist. I like that answer, right? You're absolutely correct. Sample size has nothing to do with validity. Validity simply means accuracy, right? And representativeness is just another type of validity. It's external validity, right? We talk about internal and external validity. So if sample size has no impact on validity, what then does sample size have impact on? We talk about validity, but another word we talk about all the time, which is what?
I think sample size has more to do with the power of the study.
Okay. And that is because it affects what?
The precision.
Precision, exactly. The question of how many people we need is a question of precision. The question of how we select those people, like sampling, is a question of validity, right? I'm sure you've seen all of this bullseye issue of image. So here you have this guy, the dots all fall in one same place, right? But none hit the bullseye. This is reliable. Reliable also means precision, right? If the result here is reliable, but not valid, because validity means you hit the bullseye. Here you have the result hit the bullseye, but it's everywhere, right? It is valid, but not precise. And by the way, we measure precision by the width of the confidence interval. So when we say that results are not precise, we mean that they have very wide confidence intervals. When we say that results are precise, they have very, very narrow confidence intervals. So if you have a very, very big study, you're going to see that it's going to have very, very narrow confidence intervals. So the results are precise, right? But they may not be valid. That's what we're saying. So it's very important to understand the difference between those terms. Validity is influenced by how we sample and measurement issues, right? Sample size primarily affect, precision of our estimates. So there's such a thing as, yes.
Before you move further, there are questions. Kindly help throw more clarity on the presence of both types of errors in a study or same hypothesis. Thanks. Someone asked the same question.
So I can't see the question you're reading. Okay, sorry, I got it, yeah. So the presence of both types of errors in the study. Okay, let me show you. Let me pull up a stop share. Let me pull up an example so that it's more applicable. Let me pull a study from PubMed. Okay. Okay, can you see my screen?
Yes, we can.
Okay. So here, this is a study we did with some colleagues at Merck, looking at exploratory analysis of clinical trial data. So in the path towards creating any medicines, there are typically two agencies that work very closely together. You have regulatory agencies, like in this case, in the US, FDA, but then you also have, HTAs, those are necessarily more concerned about, issues of reimbursement and issues of payment, right? So that's what health technology assessment agencies do. They like, okay, the regulatory agencies like European Medicines Agency has approved this drug. All right, who are we going to pay for to get this drug? So these two agencies are looking at very different things. Regulatory agencies are looking at, does this drug issue two major things: safety and efficacy. Does this drug work? And is it safe? That's what FDA is looking at. That's what the European Medicines Agency is looking at. That's what NAFDAC is looking at, right? Safety and efficacy. But HTA agencies are looking at very, very different things, issues of cost and issues of, equity and all of that. So what happens is that when you release results from clinical trials, HTA agencies would sometimes ask you to perform subgroup analysis, like, and sometimes numbering into hundreds, if not thousands, of subgroup analysis, right? Because they want to justify why they should or should not pay for that medication for a particular subgroup. So what we did in this study was to look at the dangers of over-interrogating the data. Like, what happens when you take a study that has been done and you subject it to the kind of analysis that are requested by HTA agencies? What do we expect? All right, because now here you have to worry about two things now. You have to worry about type 1 error because of over-interrogation of the data. But you also have to worry about type 2 error. So that's essentially what we're trying to do. So we took a clinical trial and we analyzed that clinical trial as per the requirements. So let me just show you some of the key findings from the study that emphasize the dangers of both type 1 error and type 2 error in certain studies, right? So this is an excellent figure. This figure shows you, so again, we took some of the studies, some of the HTA assessments that were done in Germany, right? Done by regulatory. Please, can we mute ourselves? Who's the culprit here? All right, thanks. So when we took all of the HTA agent, HTA evaluations that had been done, you realize that in some of them, they analyzed populations were as small as 6.9% of the original sample size that was required for the full analysis. Imagine that the original analysis required 1,000 people, right? Because remember, when you're doing a study, you calculate sample size. The sample size tells you that you need 1,000 people. You do the study, you find the result. Then another person comes along, or the HTA agent now says, oh, we want to do a subgroup analysis among this subgroup. But this subgroup you're asking for is just less than 10% of the population. So you're talking about less than 100 people that you are using to analyze for an effect that we had calculated sample size and determined that we need 1,000 people. That, of course, you might end up coming up and showing that, oh, there is no significant difference, right? The treatment has no effect. And that's dangerous, because based on that, you now say, we're not going to pay for that treatment among that group. Like, that is a very dangerous thing to do, right? So in this case, what we're worrying about here is both type 1 error and type 2 error. Type 2 error because you have very small sample sizes, right? The sample sizes do not meet what we had required originally in the original clinical trial. And so the chances that you are going to find something significant are very, very small, right? And then the fact that you also have multiple groups, because this is what we call here the problem of multiplicity, right? You are having so many groups that you are comparing, like I said earlier, in some cases you might have hundreds of groups that you are required to do subgroup analysis for. That is multiple comparisons. So you might end up finding something just because you are looking so hard. So in this case, you can see how you have an issue of both type 1 error and type 2 error. And this could also apply in just regular studies too, because you end up, you take a study that you're looking at and you end up having a scenario where you're saying, oh, we're looking at this subgroup and that subgroup, and you end up looking at like 50 subgroups, right? And your sample size to begin with was not even large. So you can see how you end up having a problem of both type 1 error and type 2 error. So that could definitely manifest in study, and then of course that comes with issues of reduced precision and power, because the sample size is now small. So you have very wide confidence intervals, right? And then of course you have small power because the sample size is small inherently. So this was just to call attention to the fact that when you do that, you end up with resulting in results that are arbitrary. So again, here, right, in this table here, what we did also was to take a clinical trial that had been published, and we reanalyzed it per the requirements of some of these HT agencies. And you'll find that sometimes your results are positive, sometimes they're contradictory. So like, how can the same study provide the results that are saying this is protective, at the same time saying this is harmful, or at other time saying there's no effect? Well, the result is that this is just noise. It's just noise in the data, right? So this is the whole point of this study, was to call attention to the fact that yes, that there's inherent danger when you do that. That there are ways we can do better, right? We should realize that first of all, that there's danger in such, and then here's our suggestions for how to improve that process. But you are scientists, right? That's why there's a need for you to understand how these things impact your studies, so that you can determine a priori the subgroups you're going to compare if you're going to do any comparisons. It's not just that you're doing your analysis and then you're like, I think it would be nice to compare this result in this group as well. No. If you're going to do any comparisons, that should have been specified in your protocol a long time ago, before you collected the data. It's not when you collect the data. Not when you collect the data, you start analyzing and you start just doing anything that comes to your mind. That is cheating. That is not allowed. Analysis should be done per protocol. But anyway, I hope that makes sense. All right. So we can move on now. again, this is a study I shared earlier, that, you know, it is scary that, you know, randomized trials published in top journals, only 34% correctly a calculated sample size. You know, that is a very, very scary statistic, especially when you consider that these are like the top journals we're talking about, journals like Lancet and New England Journal of Medicine and BMJ, and, you know, so it's like, wow, if such a high error rate is occurring in this kind of journals, then it's just crazy when you think of what's happening in other journals that are not as top tier. And so it's clear that sample size calculation is a very important skill we need to harness and to improve on and to become experts in. So what I had done was, you know, the sample size exercises I had posted were pulled from this site. I had looked for some of the, you know, some of the toughest challenges I could find, and those were some of the questions that had been asked by actual people who wanted actual results to their study. So let's go through some of them. We went through a few of them the last time, but again, I'll repeat because we have some new people in the audience. So this one was sorry, is there a question? Okay, maybe not. So this one was a question asking for sample size calculation for a 4-arm trial, right? And this is what is represented here. So here they have one experimental arm, and they have 3 control arms, or, you know, 3 standard arms, according to the question. According to the question, in the one control arm, the prevalence of the outcome in that control group is 60%. The effect size they wish to see is a 20% reduction in the experimental arm. So they want the prevalence to reduce. They expect to see a reduction from 60% to 40%, right? So the question is, if I have these arms and I want to see this reduction, what is the sample size that I need for my study? One of the things you have to worry about so just talking a little about the technical aspects now. When you have multiple arms in a study, one of the things you have to worry about is multiple comparisons, right? So if you have just 2 arms in your study, you have only one comparison. So if you have arm A and arm B, you are only comparing A and B. So of course, that's reciprocal. A versus B is the same as B versus A. So it's just one comparison. When that increases to 3 groups, A, B, and C, now you have 3 comparisons, A and B, A and C, B and C. And as the number of groups increases, we still have this error in the slide. Then as the number of groups increases, then the number of comparisons increases, right? So now you have, with 4 groups, you have 6 comparisons, right? This should be C and D. So this is a typo. And so we can express that generally with this equation. This is the equation that tells you the number of comparisons that will be in your study. So if you have n number of groups, the total number of comparisons that you will have will be represented by the equation n factorial all over 2 factorial n minus 2 factorial, right? So if we express it here for 3 groups, n is 3, so that will be 3 factorial divided by 2 factorial all over 3 minus 2 factorial, that will be 3. So this is one formula you need to know, because why do you need to know it? Well, you need to be able to adjust. You need to do you need to be able to explain what's going on, right? So of course, the Chisquares application does everything for you, so you don't have to worry about that. And you don't have to know the formula, but you should know that the more groups you have, the more arms you have in your study, right? The more the need to adjust for multiplicity. Remember, multiplicity is when you're comparing many things. A versus B, A versus C, C versus D, right? So you have to adjust for that. And how do we do that? Well, we make it more stringent for us to declare that something is significant, right? So we take the nominal p-value. Nominal p-value is p 0.05. I will make it even smaller by dividing the nominal p-value by the number of comparisons. So in the case of where we have 3 groups, 3 comparisons rather, we are dividing a nominal p-value, which is 0.05, by 3, so that our adjusted p-value, which we call the Bonferroni adjusted p-value, is now 0.017. And so when we say that a result is significant, we are judging it not by 0.05, but by 0.017. So that is what we call the Bonferroni adjusted p-value, right? And the smaller the p-value required, the larger the sample size. So that is why this is how that is tied to the p-value. So that means that the more groups you're going to compare, the smaller the p-value you're going to impose based on the adjustment, and the bigger your sample size will have to be. So that's the whole, without going into the theory, that's the whole essence of why you need to adjust for that. So let's show how with this example we have here, how we can calculate the sample size on the Chisquares platform. But any questions so far? None, okay. All right, so let's go ahead and calculate that. So we start new sample size. We select comparative study with 3 or more arms and with percentage as outcome. So that's the first thing we do there. The prevalence of outcome among control group. If we go back to our slide, this is the standard arm 1. The prevalence is 60% based on the narrative or based on the question that the person posed. So okay, somebody asked, go over the question of multiple comparisons. Let me finish this and then I'll go over the issue. And maybe you can also get an answer when we review that. So 60% is the prevalence of the outcome among the control group. So we enter 60% here. Prevalence of outcome among control, we enter 60. Then the next thing is, we have provided you with a lot of options for you to define your effect size. Remember, the effect size is the minimum gap you want to see between the treated group versus the control groups, right? So the question is, what is that? How are you defining the treatment gap? Well, in this case, it's already defined for us, right? This person says they want to see a prevalence of 40% in the experimental arm. So we can just go ahead and put the lowest prevalence of the treatment groups is 40. And then the rest are standard. Level of confidence is 95. Number of arms is 4, because we have 4 arms there. 1, 2, 3, and 4. That includes the experimental arm as well. The power is 90%. The anticipated response rate or compliance rate, let's say 60%. And then here you're going to check whether or not you want multiple comparisons. Let's say we say we don't want to do multiple comparisons, and we get result. Okay, let's say one of our parameters is invalid. Let's see. So we have percentage outcome, 60% this. Oh, okay. This is invalid because we provided odds ratio of, it's impossible to have an odds ratio of 40%. So we've tried to protect you from yourself. So what you should select is this one, and then get results. Let's see. Lowest prevalence of treatment groups, 60%. Let me refresh this page. Maybe it's still sticking on with the old. So we'll put a lot of validations into that so that when you come with a result that is beyond normal expectations, so that you don't get a result that does not make sense, right? So 40%, 60%, that's among the control group. The prevalence of outcome here is 40. Level of confidence is 95. This is chose the wrong study. Comparative study with 3 or more arms. All right, so 40. Lowest prevalence of treatment groups, we entered that as, so 60 here and 40 here based on the question asked by the person. Level of confidence 95. Number of arms is 4. Power desired is 90. Let's see. So we need 583 individuals per group, and we have 4 groups. So we need 2,332 individuals across the 4 groups, right? If you can choose any of these other options, but you have to obviously provide a number that makes sense. If you say you are looking at prevalence difference, let me explain what these are. The first one is you are saying what is the percentage of the outcome among the treatment group. So that is what we're saying here, right? This is 40. Prevalence difference is saying what is the difference between the control group versus the treatment group. So in this case, if I'm looking at the differences in prevalence, then what I will enter will not be 40, but 20, right? So in that case, if I said prevalence difference, what I will need to enter here then will be 20. So let's enter 20 and let's see the results, right? So now we have a prevalence of 484 persons per group for a total sample size of 1,936 across the different groups, right? So then the next one will be the odds ratios between the treated and the untreated. So let's say we want an odds ratio of 1.5. So with an odds ratio of 1.5, we require a number of individuals per group as 37, and then times 4, that'd be 148. So you can play along with this and try and alter the different parameters, right? And see how that influences your sample size. So if, for example, I'm interested in let's say this particular calculation, I might change different levels of the prevalence. For example, I have 3 groups here, and so I could provide the prevalence for group 1, group 2 as different possible scenarios to see what the sample size might be. So that way, let's see. Why 30% anticipated response rate? Well, I use 30%. You should base this on, this response rate should be based on what you think will be the compliance rate in your study. In general, clinical trials have high compliance rate because people are there, we're following them at the exact same time. But you can pick a value that you think works best, right? And so here, in this case, let's go back here. Lowest prevalence of a treatment group, 60 and 40 here, right? But keep it at 60% response rate. Now, don't try to be too optimistic, right? I can change the response rate and see how that affects my sample size, right? Now don't try to be too optimistic. Don't try and say, oh, we're going to achieve a response rate of 100%. You have to acknowledge that there will be some non-compliance in your study. There will be every study has attrition, right? So you can try and estimate what that attrition level might be, maybe based from results of a pilot study. Maybe you did a pilot study and you found that, okay, most people found the treatment acceptable and most people actually stayed on treatment, right? And if your compliance rate from your pilot study was 80%, well, you can go ahead and put 80% and you have a justification for why it's 80%. And of course, that will reduce the sample size you need, right? So you can try different scenarios and see how that affects the sample size for the study. And then you can decide on what makes sense for you to go ahead with. I hope that makes sense. Okay. So using prevalence difference achieves a different answer. So so if you have 60% and you have, let's say, lower prevalence of, lowest prevalence is 40%. Let's go back to that. And then we now say, so let's try and replicate that again. So with the lowest prevalence, right, we have 60 and 40. And then prevalence difference. Right, so here we have 182, 728. And here we have 219, 876, right? So why do you think that those kind of things influence the outcome? Any thoughts? Like if you entered an odds ratio, for example, right, of 1.5, and you try and calculate that, and you enter the prevalence ratio of 1.5, and you calculated that, why do you think that the results change from, let's say, one indicator, even though they sound alike, right? Why would that be the case? Because those are not necessarily identical constructs, right? For example, if we're talking about odds ratio versus prevalence ratio, they're similar, especially when the outcome is very, very, rare. Those two may be interchangeable, but they are not necessarily mathematically equivalents of each other. And so you will expect smaller differences from one indicator versus another. Try and use the indicator that is most aligned with how you're going to analyze the data, right? And so, for example, if I'm doing a case control study, I would rather use odds ratios, because in the case control study we use matched odds ratios for analysis. So you can be sure that the different ones will give you slightly different estimates, and that's why you want to compare to make sure that you get what you're looking for, because the prevalence difference could be in either direction, right? Prevalence difference of 20 could mean that you are looking at the prevalence of 60 versus 80 or 40 versus 60, right? It could be anything. So the more precise you are, then the better, the more robust the results you're looking for. So given a choice of, let's say, 60 versus 40, if the absolute prevalences have been provided, that would be the best, because there's less ambiguity about what we're talking about, right? Because here we're saying the prevalence is 60 and the control is 40 or vice versa, right? But saying a prevalence difference of 20 relative to the control group will mean I'm either saying the experimental group is 80 or that experimental group is 40. So now you see I have a different interpretation. So if you calculate the sample size for 60 versus 80 versus 60 versus versus 40, there are obviously differences, right? Those two things are not the same. So the more precise you are, the more accurate. I would have thought that prevalence difference will result in a higher. So prevalence difference, again, remember that it is whatever you specify here. So let's go back to the formula. Those are very good questions, but let's go back to the formula and look at what is going on behind the scene. So this is the formula for calculating sample size for a multi-arm trial, right? N is the total number of total sample size. The K represents the number of groups under comparison. So in this case, K is 4, because we have 4 arms in our study. K minus 1 denotes the degrees of freedom. Alpha represents the alpha level, which is typically set at 0.05. And this is the mechanism by which the Bonferroni adjustment influences the sample size. Because when we have a Bonferroni adjusted p-value, right, the alpha level would now become much, much smaller. And with a much smaller alpha, that means that we will need a much bigger sample size. Beta represents the type 2 error, and 1 minus beta is the power. The theta is the non-centrality parameter, which is the most important thing here when we're calculating sample size for multi-arm interventional studies, right? So this is the major difference when we're calculating sample size for 2-arm studies versus multi-arm studies. This parameter here, the non-centrality parameter, right? So at the end of the day, the issue that you have raised has to do with how we are capturing delta, right? Because delta is the magnitude of a difference on the Axine scale. It's not necessarily what we're measuring it on. It's not we take that whatever difference has been reported, and the difference in the context of a multi-arm study is measured on Axine square root scale, right? So when you convert those scales, whatever absolute things you've measured on that scale, small differences could translate to much wider values. And that's why that's the whole point of trying to make sure that you test, have a sensitivity table. I think I showed this earlier. You have a table like this one here. If I can find it. Right. This is a sensitivity table that will say, okay, when I provide a prevalence of this and prevalence of that in this group, this is what I find, right? So bottom line is that the more specific you are, right? The more specific you are, the more, easy to interpret the number you're saying, right? So given a choice of prevalence difference or the actual prevalence estimate, I will always go with the actual prevalence because, again, like we mentioned earlier, the difference between, let's go back to the slide here. Yeah, given a prevalence difference of 20%, right? 60 versus 80 and 60 versus 40, those are very different things because we're looking in relation to the comparison group, right? We have a fixed reference group that we're trying to anchor. And so again, remember that we're saying, is this a superiority trial, right? Where we're saying the treatment we're looking at is under the null alternative hypothesis. We're saying it is better than the control group. So the direction matters. It's not as if that the direction does not matter. It does matter. And so that's why the more you are more precise about the prevalence, the better for you. All right, so let me see. Are there any other questions in the... Is there a possibility that the 3 standard arms can have different prevalence? Yes, definitely. You're gonna have a scenario where the 3 have, and this is, let's look at the second example that addresses the issue you've raised. But I want to make sure that there are no other questions I have missed. Yes, the sample size is adjusted for multiple comparisons, and we use Bonferroni adjustment. And so in the sample size app, you have the option there to select that checkbox that indicates that you're going to do multiple comparisons, and that will automatically adjust the sample size for the multiple comparisons. And again, that has to do with the value of alpha, right? So when you specify that multiple comparisons will be done, we divide the nominal alpha, which is 0.05, by the number of comparisons, and that gives us the Bonferroni adjusted p-value. And of course, you have a much larger sample size required with that kind of adjustment. All right, let me see other questions that I have not answered. All right. How does number of arms? How does number of arms affect block randomization? Do I need to mention the number of blocks depending on the arms in the study to make my calculated sample size? So block randomization essentially is that's a good question. There are different ways to randomize, right? Randomization will not necessarily result in equal sample size, so that's very important to know. And so when you assign people at random, so let's say I have 4 arms in my study, and as people are coming, I am simply just assigning them at random to you go here and you go there. I will end up having a study where the arms are very different in size, right? And that's the whole idea of doing block randomization. Block randomization says, that we assign at random to the groups. We start at random on the group, and we assign in blocks so that the whole idea behind block randomization is to result in groups that are much more closer in size, right? And the reason why we care about the sizes being approximately the same is because statistical power is driven by the smaller arm, right? So if I have let's keep things simple. If I have 2 groups, right, group A and group B, and group A has a much smaller sample size, not only does that affect precision, that also affects power, because remember that power is driven by the smaller arm, right? So we need to make sure that our groups are as, evenly sized as possible for that reason. So with this calculation, we are assuming that of course you're going to do block randomization, because the sample size per group here, you just multiply that by the number of groups to give you the total size, right? So that assumes obviously that you are going to have roughly sized, groups. But of course, in reality, it's impossible, almost impossible to ensure that the arms are like identical in size, right? It's quite hard to pull that off. But again, sample size is all about estimations. It's not all sample size calculations are wrong, right? Some are useful. You can think of it that way. The same way we talk about models. All models are wrong, some are useful. So, but with that, at least that gives us a closer approximation to what we need to achieve for us to get results that we are looking for. So let me see, what else is there? Is there a possibility that the 3 standard arms can have different prevalence? If so, how do you calculate the sample size? So what you do in that kind of case is what we showed here in the sensitivity table. You calculate the difference. You take AM1, AM2, AM3, and 4, which have different prevalence estimates. You calculate the sample size as needed, and then you can say, okay, based on the three different arms, these are the varying different sample sizes. And for you to be more conservative, of course, you have to go with the higher sample size, assuming you have the resources, right? If you don't have the resources, well, you can argue for why you are going with, the smaller arm size, right? But that is what you should do in such a case. So option number 1, you can provide sample sizes for the different arms. Option number 2, you can take the average of all of them. So in this case here, let's go back to that arm. So in this case, I could take the average of standard AM1, standard AM2, and standard AM3. The average of them, I would then put in my formula here, so that when the prevalence, if I'm talking about the prevalence of outcome among the control group, instead of 60, I could put, let's say the average is 55, right? And then the prevalence of the treatment group is 40 again. The level of confidence is 95, number of arms is 4, the power is 90, the anticipated response rate is this. And now this is my sample size based on the average. Of course, it's going to be different than if I had used the lowest group or the highest group, right? But the average is at least more conservative. It's a more conservative approach to take. All right, let's go to the second example. So this one is a bit similar to the previous one, but the only difference is that instead of having multiple control arms, here we have multiple intervention arms. So we have 1 control arm, and then we have 2 treatment arms. You remember in the previous one, we had multiple control arms, and we had 1 treatment arm. Here is the other way around, but the same principle applies, right? We can only have 1 number to use in our sample size calculation. So here we can either take 1 of them, or we can take the average of them. So I have a pop quiz for you here. With many treatment groups, we need 1 number to represent all the treatment groups in calculating the effect size, right? So if this is a control group, and this is the lowest of the treatment groups, and this middle bar is the average, and this is the highest, right? The question is, which of the treatment options is most likely going to yield the biggest difference between the treatment and control groups? What do you think? If this is the control group right here, and you have lowest, middle, highest, which gives you the biggest difference between the control and the treatment? No thoughts?
Highest.
Okay, somebody said highest, the lowest. Why do you say highest?
highest is farther from the control group.
Exactly. So it's just, we're talking about the absolute difference now, right? So yes, this is the farthest difference, right? So yeah, you're absolutely correct. This will give us the biggest difference. Now the question is, which one should we not use? If we were to say that there's one of those that we should not use at all, which one would that be? Okay, and why? Why should we not use the highest? Yeah, see, some of you said higher. We should not use the highest, right? But why?
It will likely give us less representative or comparative value with the sample or control.
You're right, but not for the reason you mentioned. You said it will not give us representative. Maybe you are trying to say the right thing, but I kind of want to say it a different way. Okay. Let's say you are the director of FDA, right? And a pharmaceutical company comes. Sorry, I keep talking about pharmaceutical, not because it's for any reason, but I think the examples are more dramatic. And they say that, oh, this drug of ours, this is the big difference we're going to deliver to you. And then another one comes and says, oh, this drug, well, we believe, we're very confident this is the difference that we can deliver. Which claim will you rather go with? A big difference or a modest difference? And remember, this is just a promise yet, right? Sorry?
A big difference.
Oh, you go with big, okay. Okay, let's say a big, let's change the word now. Let's say, instead of saying difference, a big claim versus a small claim. Which one will you go with?
Big claim.
I'll go with the small one because the largest is most likely to be not true.
Okay. Let's look at it another way, right? Let's say let's say a very dramatic claim that the pharmaceutical company says this drug will raise the dead. Or this drug will just cure a headache, right? Which one is more believable? The exaggerated claim or the realistic and modest claim?
The modest claim.
The modest.
Realistic and modest.
Yeah. That's why in public health or medicine in general, we want to err on the side of caution. We don't want to believe your drama, right? So we would rather believe the thing that's more believable, right? And that we say in general, we say that we want to be more conservative. That's a technical or professional way of saying it, right? Science strives to be conservative. And by conservative, what we actually mean is that we would rather believe in something that is modest but believable than something that just feels like hype, right? Science is not one to like believe in hype that is realistic, like somebody clearly said here. So that is why when you're calculating sample size, right, we would rather go with the average of all of them or the lowest, right? And that's why on the Chisquares app too, right, we say this first indicator says if you have multiple treatment arms, provide the lowest prevalence of the treatment groups or the average of them all. What we're just saying is that please don't give us this number. Give us the average or give us the lowest, because this one will end up, the claims are just not consistent with reality, and that's why we just want. I mean, they may be true, but it's it's more likely that this is realistic and this is realistic. So in general, you want to stick with the lowest or the average. And so the sample size here is the same thing, right? If we go back to the picture, so here we have group A, the prevalence is 50. And here we have the prevalence of 25 for group B and the prevalence of 37.5 for group C. So the average of 25 and 37, I'm not sure what that number is, but let's say we'll put as 30. We'll put the other parameters that we need. Here we have 3 arms, so we're going to put 3 here. And we'll get results. And so this is what we need for our study. We need 107 people in each group, or 561 for all 3 of them. Any questions on that? Let me stop and take questions. I think that is a bit straightforward, but if you have questions, please you can type them in the box and we'll answer them. Okay, none. Great.
Thank you so much, Dr. Gaku. Could we try calculating for 2 groups?
Okay. If you have just 2 groups, like a control and a treatment group.
Yes.
Okay, in that case, we don't need this formula. We can just go to oops, sorry, I've been logged out. So in that case, we just go to comparative study with 2 arms. The prevalence here is, let's say we said was 50, I believe. The prevalence of outcome among the control, let's say, was 30. So you see here, it doesn't ask you about the lowest of the treated or the average of them all. It just says what's the prevalence among the treatment group, because there's just one treatment group. The level of confidence desired, is the test one-sided or two-sided? We say two-sided because two-sided expects that if we are looking at a superiority trial, we are saying that it could be that the treatment is better off than the control, or it's actually worse off than the control, right? So that acknowledges that it could go either way. Of course, a two-sided test needs more power. Imagine like you're driving a car and you want, the road bifurcates and you want to go both ways. That means that you have to drive to one side and then you have to drive to the other side. You need more gas, right? So the same way, if you want to do a two-sided test, you need more sample size to do that. And then you will then, put the response rate and you get results. So that would be how you would calculate that if you had only 2 groups, because then you don't have to worry about multiple comparisons. The formula is drastically different as well for calculating sample size between 2 groups versus 3 or more groups. And that is because we don't have to worry about one parameter called the non-centrality parameter. The non-centrality parameter is simply imagine you have a bunch of keys and you are trying to, you only have one chance to open a treasure chest with these keys. Think of a non-centrality parameter as this stuff you have on the keys that helps you identify which one is a correct key, right? When we are doing sample size calculations for multi-arm studies, we absolutely need to figure out the non-centrality parameter, which is a very complex statistical procedure to calculate the NCP for a given number of arms, right? That is what makes sample size calculations for multi-arm studies quite complex because it's just complex enough its nature, because there are so many things we need to account for that we will not even worry about if we're not having multiple arms, right? That's why you can see the formula for a 3-arm or more study quite complex, because there's a lot going on into those formulas. Is that clear?
Yes, thank you so much, Doctor.
All right, you're welcome. Okay. In equivalence trial, okay, that is the power can be anything. The power can be 80%, so we definitely recommend the power of between 80 and 90%. But we'll come to equivalence trials in a minute, because those are quite different from superiority trials. All right, if we're all happy with this part, we can go to the next question, which is the cluster randomized trials. Now, this one is different. The question here was, I am doing a sample size for a 3-armed trial to assess which type of delivery methods lead to higher ownership of mosquito nets in an African community. All I have found on the internet and in books refers to 2-arm trials, and I can't find any information on calculations for multi-arm trials. So the issue here is it's not just the 3-arm trials. It is also the issue of clustered. This person just trivialized this sentence there and focused on the multi-arm study. But a bigger concern here is even that it's clustered. So this is a cluster randomization, right? In most trials, what you have is that you're randomizing individuals at the individual level to treatment or control. In a cluster randomization, you're randomizing groups. And why might we want to do that? Well, because you're trying to, it is sometimes just logistically impossible. Like, look at the example they gave here, right? They are trying to see which kind of transportation method delivers the highest net to a community. So you know, if a community is by the riverside, logistically, it just makes sense to deliver it by boat, right? Or you might just have a contract with the truckers and say, please, this is your route. Just deliver this net every day to this community. It is just logistically easier to assign the treatment, you know, in groups, as opposed to saying this guy in this house will receive it by boat, then the guy in the next house will receive it by lorry or truck, and then the other guy will receive it by bicycle. That results in a lot of, it's just a logistical nightmare, right? And it also results in contamination, because if the guy who is supposed to receive it by boat doesn't get it in 2 days, he would just go to his neighbor and say, guy, how do you get your nets, right? And how can you connect me with that guy who is delivering for you? Now you already have contamination in your study. So in some cases, you have to worry about cluster randomization. Now, the problem with clusters, however, is that you have intra-cluster correlation. People in the same cluster will tend to behave alike, talk alike, and, you know. So the question is, how are you sure that the differences you have seen between villages A, B, and C are because of the treatment and not because of just their similarities or differences as a group, right? Because people don't live in group village A or village B at random. They chose to go there. And so the intra-cluster correlation makes it a challenge, which we need to account for specially, right? So that is what is, you know, so in this kind of study, we have to worry about two things now. We have to worry about the fact that it's multi-arm, there are 3 arms. And then, in addition to that, we have to worry about intra-cluster correlation, right? Because what intra-cluster correlation does is that it kind of it reduces the diversity of our responses, right? Because if people in the same cluster talk alike, behave alike, do everything alike, if we asked 100 of them a question, think of them as being clones of each other, all right? If everybody in the village is a clone of each other, or let's make it less dramatic. If every second person in the village is a clone of the first guy, and we've administered 100 questionnaires, what we actually have is not 100 questionnaires, but 50. Because they are literally clones. Every second guy is a clone of the first guy, right? And so that's the problem with intra-cluster correlation. The responses have, you know, less variance, you know, they as opposed to had they been at random at the level of individuals. So we have to account for that when we're calculating sample size for clusters. So again, put very simply, the apple doesn't fall far from the tree. Again, emphasizing the idea that people who are from the same cluster may share very similar traits that may be different from people from other clusters. So how do we account for this? We do that with a construct called the design effect. So put simply, the design effect is a multiplier that kind of like penalizes clusters for having higher intra-cluster correlation. So the punishment comes in the form of increased sample size, basically. So if we say a cluster has an intra-cluster correlation of 1.3, that means that in simple terms, we have to increase the sample size by 1.3, right? But in more technical terms, what we mean is that the variance of have we done a random sample, not at level of groups, the variance will have been 1.3 times higher with a simple random selection than what we have with the cluster. But the take-home message really is that the design effect will have to account for the reduced diversity of responses by increasing the sample size by a factor of the design effect. So like I said, design effect of 2 means that you have to double your sample size. A design effect of 3 means you have to triple your sample size, and so on and so forth. The design effect cannot be less than 1. And, you know, 1 actually is the design effect for a simple selection of random selection of individuals. So the design effect has to be more than 1 in a nutshell. So how do you get the value of the design effect? Well, you can You can guess the value. You can just put in a placeholder like 1.5, a value between 1.5 and 4. So you can, again, that's where sensitivity tables come in, right? You can say at the design effect of 1.5, this is what the sample size I get. At the value of 2, at the value of 2.5, at the value of 3. So that's one way you can do it. If you are very adventurous, you can calculate it by yourself. The design effect is very simple to calculate, actually. This is the formula. The formula is, 1 plus the delta multiplied by m minus 1, where the delta is the intercluster correlation and m is the average cluster size. Of course, this is a very simple formula that assumes that all the clusters are averagely sized. There's a more complex formula that we use when the clusters are radically different sizes, but that's talk for another day. So once you get the average size of a cluster, you just plug that in and you calculate the design effect. Now, question then is, how do you know what the intra-cluster correlation is? This is a very simple way of thinking about it. You can think of it as the ratio of what's the probability that two people that are randomly selected from the same cluster will have similar responses due to chance, divided by the probability that two people randomly selected from different clusters will have similar responses due to chance. So in other words, I'm saying that if I pick two people from, if I pick two people, right, let's say I have cluster A and cluster B. If I selected two people from cluster A, what is the chance that the responses they give me to a particular question will be similar just purely due to chance, right? And then what if I picked two people now and again, but one from cluster A and one from cluster B? What is the probability that their responses will again be similar purely due to chance? So that's how you can estimate it. But in practice, nobody calculates design effect. They just use default values like 1.5, 2. You just come up with a sensitivity table and just plug in values more than 1.0. So you can start from 1.5 and you can just look at the possible impact on sample size. So unless you're really, really adventurous, I wouldn't worry about all of that of how am I going to come up with a value for the intra-cluster correlation. This is just providing with a theoretical aspect so that you are aware of what's going on. But that's the design effect in essence. So let's go over and let's calculate that sample size for that. Of course, there are several factors that will affect the intra-cluster correlation. It will depend on the size of a cluster, for example. It will depend on several other qualitative reasons, qualitative factors like, is the cluster like a family? How well do they know each other? So it's not just pure science, right? Just think of it like just everyday stuff. Why would two people give you very similar responses? Well, it depends on if they've known each other for how long they've lived together, whether they are very good friends, the level of relationship, their social networks, their shared values. I mean, all of those things come into play in determining whether or not the response will be similar. So it's not just some esoteric stuff. It's just day-to-day stuff, right? So you can think of 100 reasons why people from the same cluster will give you similar responses. So let's calculate the sample size now for that. So in that case, we'll come here. We'll come to cluster randomized trials. We'll select 3 arms with percentage as outcome. And then let's look at our parameters there. Okay, we don't have any, but we can just just go through some hypothetical numbers. So let's say the prevalence of outcome among control group is 30. Again, lowest prevalence of a treatment group we say is 30. It's 50 and then 30. Level of confidence, number of arms is 3. This is where you see the design effect. This is the one thing that is new here. We're accounting for the design effect here, right? And again, we've provided an explanation of what a design effect is. We say that, let me expand this. The design effect is a multiplier that accounts for clustering in surveys, penalizing them for similarities within clusters. So in simple random surveys with no clustering, the design effect is 1, which is the lowest possible value. But you can put values between 1.5 and 4. This is not a survey, but the principle also applies here. Design effect applies wherever you have cluster selection, whether it's in surveys, whether it's in cluster randomized trials, or wherever. So you have to account for that. So, like I said earlier, have a sensitivity table where you say, okay, a design effect of 1.5, the sample size is this. At a design effect of 2, the sample size is this, right? At a design effect of 2.5, the sample size is, this. Of course, as the design effect increases, the sample size will increase as well, because that is the whole point of a design effect. It's penalizing the clusters for being so similar to each other, and so you have to increase the sample size. Yes, design effect applies to observational studies as well. So if you are doing a survey, a cross-sectional survey, and you are doing cluster sampling, so bottom line, wherever you have cluster selection of anything, you have to worry about design effects. How about that? So whether it's an experiment like a cluster randomized trial, or whether it's a survey where you're selecting clusters, as far as you're selecting clusters, you have to worry about design effects. So I hope that is clear. Alrighty. Now let's go back to the other scenarios. The other scenario was how sample size was to demonstrate the fact that sample size is agnostic of population size, right? So the point is that whether you are calculating sample size for 1 million people, right, or for 100 million people, it doesn't matter. So this is the example I used here. If I have to calculate a survey, sample size for a survey for Boston, which is a city, or Massachusetts, which is a state, or for the United States, which is a country, or for the whole world, it does not matter the population, right? So the sample size will always be the same. So sample size is agnostic of the population size. So let's show that, for example. I have a cross-sectional study with percentage as outcome. Let's say here the population size is 1 million, right? Oops. 1 million and 1 million people. So I'm not going to change anything. I will just change the population size. So we'll see. I get results 481. I add an extra 0. I get results 481. Add another extra 0. I get results 481. Like, I can keep adding all the zeros in this world. The sample size will not change. It will be 481, 481. Sample size is agnostic of population size, right? Now, that is at a point, right? The question is at the point. Let's put the sample size. 347 now. What has changed? The population size so that's why we say at a point. And what is that point? Let's go back to our slides. This is this point here. The assumption, the underlying assumption in sample size calculation is that the sample, which is this, is infinitesimally smaller than the population, right? That is the assumption we're going on when we calculate sample size, that this sample is so small compared to the population. Now, we can't just say infinitesimally smaller. We have to go with the number, right? In science, we'll just go with the number. So the question is, what do we mean that it is infinitesimally smaller? Well, if your sample is smaller than 5% of the population, then anything above that does not matter, right? So as far as it is smaller than 5%, whether you can keep on increasing the number forever and ever, it does not matter. The problem happens when your sample is 5% or more of this. So in other words, we're saying that when your population, this sample is no longer infinitesimally smaller, right? When it now becomes bigger, now we have a problem, right? because this assumption has been violated. It is no longer infinitesimally smaller. It is 5% or bigger, right? Now, we have to now correct for the violation of this assumption. Remember, the assumption was that there is infinite, this population is infinitely smaller than this, but it is no longer infinitely smaller. In fact, it is finite. You know, finite means that it is fixed, right? It is so large now that this assumption is violated, and so we have to correct for it, and that is what we call in survey methodology finite population correction. So if you look at the sample size formula for a survey, you can see there's no population size here. There is no saying, you know, the denominator of a population. The only reason why we ask you to provide the population size is so that as we are calculating the sample size, we are trying to compare it to the population, and we're saying, has this assumption been violated or not? So whether it's 1 million people or 1 billion people or 10 billion people, that sample size, that population is still smaller than 5%. As far as it does not cross that threshold, the population can keep going bigger and bigger and bigger, and it does not matter. The only time it matters is when your population size is rather small, right? And we can say that, wow, okay, this sample is no longer infinitesimally smaller than the population size. Then that is when the finite population correction kicks in. And that is the only time the population size matters, is when you have a rather small population and you have to draw a sample, right? And so that is why we provided a default value of 1 million. And that's why in the hint here we say a rough estimate will suffice. If unknown, please enter 1 million. And so sometimes people get themselves into a bunch. They're worrying like, gosh, I want to calculate sample size for a country, and I don't know the population of the country. I'm like, it doesn't matter. Just put any big number. Just put a million. That's fine. It doesn't really matter whether the country has 25 million people or 300 million people. It makes no difference. Are there any questions on that? Or is that clear? Okay, that's
the question from 1.5 as the, oh, okay. You
that's an answer to somebody else's question. Okay. All right, let's move on then. Sample size for...
Yeah, thank you so much. How do we define a finite population? And I've seen some sample sizes where they first calculate using the Chisquares, the common cross-sectional studies, and then they control, they recalculate for a finite population using a formula. How applicable is that?
Any decent sample size calculator should do that automatically, so you don't have to worry about it.
Oh, okay. On the platform, thanks.
Yeah. So any app that is worth its salt should those are things that should do automatically in the background for you. So of course that's done on the Chisquares platform too.
Sure, thanks.
You're welcome. Yeah. Any other questions? No. Please, I'm not saying the sample should be 5% of the population. In fact, you should not worry about that 5% number. I'm just trying to explain to you what goes on behind this. The sample size should be what you calculate from the app. I'm just telling you that there are some adjustments that goes on in the background, right? And the 5%, in fact, please forget about the 5%, right? You don't need to know that. I'm saying that the finite population correction kicks in when we determine that your sample size is 5% or larger of the population, right? That is the only time the population size matters. So when we ask you in the sample size app, what's the size of a population? You have to realize that the sample size formula does not have n in it. There's nowhere in that formula where we say, let me go back to this. There's nowhere in the formula that says population size. No, it's not. So population size does not even come into play when we are calculating sample size. It's not needed. We only use it to correct for the finite violations of the infinite assumption. And that's what we call the FPC, finite population correction, because now your sample is finite related, your population is finite relative to the sample. We want to assume, at least statistically, that your population is just infinite. It just goes on and on and on and on. So that your sample is just a very tiny proportion of that infinite population. But should we now determine that, oh, this assumption is violated, this population is no longer as infinite as we assume, is actually quite finite. Then we have to calculate the correction for that, which is what goes in there. So no, I'm not saying that your sample size should be 5% of your population. You should come into the app and calculate your sample size. And then we will determine whether that assumption is violated. And we will, so this number you have here, adjust for anything that needs to be adjusted. So you don't have to worry about all of this. But this is an academic environment where we're talking about not just it's not just a demo. We're also talking about the technical considerations, right? So that's why those discussions come into play. I hope that distinction is clear. Okay, alrighty. All right, let's go to the next calculation, which is, why am I having this stuff on those lines? Like, how does that happen? I'm not sure what's happening. Okay, great. I am very perplexed about this line, this red line. I'm not sure what that is, but anyway, that's fine. The sample size for a retrospective cohort study. So a retrospective cohort study, and a prospective cohort study, and a case control study all have the same sample size calculation. So if you know one, you should know all. But I thought I would just explain the difference between those three terms, what they mean, because people get confused about them all the time. In all three of them, we have exposure, exposure, exposure. The exposure always comes first, right? Exposure will always come before the outcome. So in a prospective cohort study, exposure comes for the outcome. Retrospective cohort study, exposure comes for the outcome. And the case control study, exposure also comes for the outcome. So the outcome comes last, because that is how things happen in nature. You are exposed and then you get the outcome. What differs between prospective cohort study and retrospective cohort study is like where we are as the investigator. So in a prospective cohort study, the investigator is here, and they were right there. Imagine that. Let's think of it as you are cooking a meal, right? If I have a world-renowned chef and I ask them to come and cook a meal and teach me how to cook a meal, and they come to my house and I'm right there with them while they're cooking, like they bring some ingredients, which are the exposure, right? The goal is to cook a dish, which is the outcome. And I am there with them right from when they unpack the ingredients, and I'm watching right there with them. And I can see how they're putting things together and everything until we cook the meal. That is a prospective cohort study. I am with the chef right from when the chef started. That is a prospective cohort study. In a retrospective cohort study, the chef is there, he's cooking his thing. Now I have to go to a meeting. So I say, oops, I'm going to just set up the video to record you while you're cooking. Then when I come, I will go back and review this video. So what's happening in the retrospective cohort study is that the exposure was there, proceeded, and the outcome was formed. Then when I come back, I am going back towards time. I'm reversing time via the video. And I'm now saying, oh, and I'm watching and say, oh, I see how he put things together. That is what a retrospective cohort. I came at the end, but I'm trying to reconstruct time by going back to the video and seeing how things progressed. In a case control study, the chef is there. Unfortunately, there's no video recording. And I only have the dish at the end. I have to now take this dish and try and piece it out and figure out what went into it. Because I was not there when the guy started. He did not leave me any notes about these are the ingredients that went in there. I did not set up any video recording, right? All I just know is that I came and met a dish, and I have to try and figure out what went into this dish. And I'm taking that part. I'm like, I think this looks like onions. oh, this looks like this, right? That is what a case control study is. A case control study, you have the outcome, and all you're trying to do is figure out what the heck is the exposure that leads to this outcome, right? In a retrospective cohort study, the outcome has already happened, right? The exposure was there, and you're going back in time. You're going back to records and, hospital notes, and you're trying to reconstruct the exposure as though you were there back in time. And in prospective cohort study, you are right there when the exposure started, and you're following along in time to see how the outcomes occur and how they differ between the exposed and non-exposed groups, right? Again, all three studies are trying to look at the same thing. What is the exposure between, what's the relationship between exposure and outcome? It's just how they're doing that is different. And also where the investigator starts from. Sample size, however, calculation for all three is exactly the same. Any questions? All right, so now let's see how we calculate sample size for the three of them. So you'd come to comparative study with two arms, percentage as outcome. Again, this is the exact same thing we talked about earlier. You provide the prevalence of outcome among the control group. You provide all of this. And again, you get results. It is exactly like what we discussed. So a parallel arm randomized trial, case control study, cohort study, and a, whether it's prospective or retrospective, exact same sample size calculation. The one thing I will note is that for case control studies, we recommend using a ratio of 4, right? For the ratio of controls to cases, right? That's the level at which you have optimized sample size for controls versus cases. Anything above 4, you are really just wasting your time because it won't generate any better, any better power. So that is the recommended level for sample size calculation. How can we identify the appropriate study type of a paper published by someone else? How can we report study that follows these designs? I'm trying to understand what your question is. How do you identify the appropriate study type? Now, please, there is a huge, one of the things you want to avoid is on PubMed, you can't always assess, there's just a lot of blunder on, some people don't even know the study they're conducting, right? If you search PubMed for something like, let's say, so when you search something like on PubMed for, let me put this in exact quotes, so that gives us the exact result. Because I just want to address that question you asked there. So it's, who can identify a problem with this study here? Specifically, I'm interested in this part here.
I think you can't have a prospective case control study.
There are just so many things wrong with this, right? It's like a prospective 2A longitudinal. It's like, what the heck? This does not exist. Like, you are just making stuff up. I think the problem is, and this, I'm trying to respond to the question of somebody asked, how do I determine the kind of study that somebody did? Please don't rely on what they said, because they don't know what they're talking about. They don't know the study they did themselves. Yeah. And unfortunately, right, this is not a rare thing. Like, you see, like, thousands of studies having this, Again, you see things like, prospective case control study. You see things like, I'm sure, like, if you search other things like, interventional. Oops. But then, right, even here, you see things like terms like a retrospective case control studies, like, case control studies by definition are retrospective. What do you mean? What do you mean retrospective case control? Is there one that is not retrospective? It's just funny. And then you see things like interventional case control study. It's like, what in the world are you talking about? That does not exist. But by the way, who can tell us why this is a huge problem? Like, why is it such a wrong thing to say? Interventional case control study. Why does that not make any single sense? Who can help us out here?
You can intervene what has happened earlier.
Case control studies, are they observational studies or are they experiments?
These are basically observational studies and not experimental studies. So unless you're talking about a randomized controlled trial, or maybe basically a quasi-experimental design, but not a case control. So it's purely an observational study. Thank you.
So when you say the word interventional, what does it mean?
You don't assign exposure case control study.
So interventional means an experiment.
Yeah.
So you see why we have a problem when you describe your study as an interventional case control studies. Like, what are you smoking, right? That doesn't make any sense. Do you know what I mean? So back to that question of how do we know? And then you also have, get worse, right? Also, the other extreme, people describe, and this, unfortunately, these are not just in small journals. Even in the biggest of journals, we see things like this. This one is describing this as a descriptive case control study. What's the problem with this? So all studies by definition are either descriptive or analytical. Descriptive means that you don't have groups being compared. An analytical study is where you have two groups being compared. Case control is obvious in the name. You're comparing cases and you're comparing controls. That should be obvious that it's not a descriptive study, it's an analytical study, right? So going back to that question of how do we know what study, the question was, how do we know the design the person is using? Please do not rely on what they wrote. Half of the time they're wrong. So you have to know, that's why you yourself need to know those things so that you can know what they did, right? And again, don't just imagine that because it was published in the Lancet, it is somehow correct. You'll be shocked. So you have to understand what the studies are, and then you have to make sense of just what the design is. So that is all I can say to that question, really, other than just like you have to understand it yourself. But the bottom line is that whether it's prospective cohort or retrospective cohorts or case control, sample size calculations for those are the same. Now, let's go on to another set of studies, non-inferiority trials. This I thought I would pay some attention to this because the sample size calculation for non-inferiority trials are quite different from superiority trials. Generally, when people would say, I want to do a randomized trial, but that is not enough, right? You want to be more specific. What kind of trial are you doing? Is it a superiority trial? And this is how you, for those of us who are not familiar with it, I just thought I would provide a visualization of what the different types of studies mean. So we have superiority trials, equivalence trials, and non-inferiority trials, right? So in general, when you hear people say randomized trial, they are actually talking about superiority trials in most cases, although, that's an assumption because maybe they don't even know what trial they're doing themselves. It's not impossible. So, but in general, you have a sense that when people say randomized trial, they're actually referring to superiority trial. So for those of you in the audience, please, you want to mind your language. You try to be as precise as possible when describing things. So if you're talking about a superiority trial, well, you should say a individual randomized parallel arm superiority trial, right? That tells us everything we need to know. So superiority trial is saying that I am better, right? So that's why you see that the delta is in one direction only. We're saying that the treatment is better. The null hypothesis is explicitly assessing that the treatment is better than the control. That's what goes on the superiority trial. And the null hypothesis, this is very important. and this impacts sample size calculation dramatically. The null hypothesis in a superiority trial is that the new treatment is not different from a standard of care, or that the difference in means is zero, or difference in prevalence is zero. You can frame that in a million ways, but we're just saying that the new treatment is not different from a standard of care, right? The alternative hypothesis is saying that, no, the new treatment is actually better. That's what the superiority trial is saying. Now let's go over to the other extreme, which is the non-inferiority trial. The non-inferiority trial is saying, I'm not worse. So it's saying, okay, this is the delta, right? To say I am worse, right? And it's saying that, oh, at least I'm not going the other direction, right? So true or false? Non-inferiority trials are one-sided hypothesis. True or false? True, exactly.
True.
Exactly, you're right, yes. Cohort studies are analytical. We are comparing two groups. Remember, exposed and non-exposed. I just saw the question pop up, so I thought I answered it. So non-inferiority trials were saying that, oh, I am no worse than the standard of care. Now, take note that the null hypothesis in a non-inferiority trial is that the new treatment is inferior to the standard of care. Take note that in a superiority trial, we're saying that the new treatment is not different from the standard of care. Why would it be a dangerous thing to have this null hypothesis here? If we said the null hypothesis in a non-inferiority trial is, how do I get this into? Is this, right? Let's say somebody says that, someone who does not understand the nuances of study design says that the null hypothesis, because they're just used to null hypothesis being that, oh, the means are the same. Why will this be such a dangerous thing to do? To say that the null hypothesis in a non-inferiority trial is that the two treatments are equal. Can anybody think of a rationale why that would be the most dangerous thing in the world? Okay, when we don't detect the treatment effect, right? Remember, we fall back to the null hypothesis. So that means that in a superiority trial, if we fail to detect that the null hypothesis is true, that the alternative is true, we will then conclude that we will then accept the null hypothesis that indeed those two treatments are not different from each other. Do you understand that? That's what's happening, right? The investigators are hoping and praying that, my gosh, the alternative hypothesis should be true. And the alternative hypothesis is that this new treatment is better than the standard of care or than the control. That's what they're begging and praying, that we want to find that there's superiority. But if we can't find a superiority, we are going to just say that we are going to go ahead with the null hypothesis, which is that the treatments are not different from each other. Now, if we set the null hypothesis of a non-inferiority trial to be that the treatments are not different from each other, well, that is what the drug manufacturer wants to see. They want to see that there's no difference in treatment, right? And under what circumstances can we conclude that there is no difference? We talked about this earlier. What is one way that you can generate results that say there's no difference? Who remembers? This is type 2 error, remember? Under what circumstances can we create type 2 error? When our sample size is
when we have a small size.
Sorry?
Small sample size.
Small sample size. So imagine a scenario, right? I'm the maker of a pharmaceutical drug, right? Let's say a drug for a new drug, a drug for, let's say, treating hypertension. And I want to make a claim that this new drug is no worse off than the current treatment. If I'm allowed to rig this with this hypothesis, right? What is it that I could so easily do? I will set up a study that has very small sample size, right? And then if all I end up doing is saying, oh yeah, the null hypothesis is true that this new treatment is not different from standard of care. Do you see why that is so dangerous? Or you still don't get it?
As well use the new treatment. But as well use the new treatment since they are not different from each other.
Yeah. And that is why in a non-inferiority trial, we have to make sure that we disincentivize you from deliberately designing a bad study. Because you don't want the null hypothesis to be true, because the null hypothesis is that, yeah, your treatment is worse. Now you have to make sure that you get a very large study to prove that you're not worse. Is that clear? And then an equivalence trial is like, okay, it's equivalent, you know. We have two boundaries, minus delta and delta. And so, but in general, the most confusing one to calculate generally is non-inferiority trial because of the reversal of the hypothesis. Now, how do we determine the delta for a non-inferiority trial? There are many ways to do that. We can use, sometimes FDA will say, recommend that this is the delta we could use. So the regulatory agencies could propose a, but okay, but there's a question here, but also that would mean H1 and H0 will be the same. No, so it's not necessarily the same. It sounds similar that, you know, so the null hypothesis here is that new treatment is inferior, right? That's a null hypothesis for a non-inferiority trial. The alternative is that it is not inferior. That's why we call it a non-inferiority trial. And so the goal is to really disincentivize you from oh, okay, just okay, I understand what you're saying. Yes, I agree with you. Yes. If you're allowed to do that, yeah, exactly, yeah. Because that's essentially what the guy wants to prove. He wants to prove that his drug is non-inferior. So if you were allowed to do that, he was like, yeah, let's do a study with 5 people. And so that is why you are not allowed to do that. That's why the hypothesis for a non-inferiority trial is quite different. I want to make sure I'm not missing any questions. So let me quickly. Okay, all right, no questions. So the delta here, in calculating the sample size of a yes.
Oh, no, I wanted to ask you to go back to slide mode. All right.
Okay. So in a non-inferiority trial, right, the biggest problem we have is calculating the value of delta. So the delta is what margin does this study have to fall in that we can say it's non-inferior. So that margin, that delta, we can get in many ways. FDA sometimes will weigh in on that, the regulatory agencies. Sometimes we convene a group of experts. If it's a drug, let's say our previous example, a drug for hypertension. Well, who better to decide that than clinical experts? We bring in nephrologists, we bring in a panel of medical experts, and we ask them, guys, what will be the performance of this new drug that you as clinical experts will say that this drug, this is the zone of non-inferiority. So we call this is the value delta, and this zone we call the zone of non-inferiority, right? So our medical experts can tell us, or we can look at the results of the initial trial and take its lower confidence interval and say, okay, at least you should meet this lower confidence interval, right? For you to be considered non-inferior. So there are many ways. There's no right or wrong way, but there are established ways of determining the zone of non-inferiority, which is what we use in trials. So again, to calculate that on the Chisquares app, you simply come over to equivalency trials. Again, the calculation is the same, but what is different is the zone of non-inferiority. You provide a prevalence of outcome among the control group. You indicate the response rate and the power and the other things as before. But here, this is the key thing here. The absolute prevalence difference. This is the zone of non-inferiority we're talking about. So if you say that I expect, 20% difference, and take note that here in this non-inferiority trial, you are not asked to provide whether the test is one-sided or two-sided, because we are calculating it as a two-sided test, So as a one-sided test in the non-inferior direction. So that's why you don't have to specify whether it is one-sided or two-sided. So you provide the values, and so this tells you that you need 134 people in each direction, right? And that in total you need 268 people in your trial. When calculating for an equivalence trial, remember that the main difference between an equivalence trial and a non-inferiority trial is that they exist in two directions. The hypothesis testing is in both ways, right? So that means that this is a two-sided test. This is a one-sided test. That is the major difference between the two of them. What do we do for studies where we don't have the prevalence of outcome in control? If you don't have the prevalence in the control group, you can use the prevalence in the population. You can use from other studies, or you can ask an clinical expert to provide you with the most educated guess. Remember that sample size is all about guessing. It's a guesswork, but it's an educated guess. So better to have something than nothing. So you can have a group of experts to say, okay, what do you think? And then you have a sensitivity table that looks at different parameters that cover the reasonable expected level, right? And that's what you could do. Let's see. We'll talk about clusters. The last sample size here we'll talk about quickly is for diagnostic tests. So diagnostic tests essentially are, sometimes you come up with a new test. Maybe you have a test for Ebola or COVID or whatever it is. And the question is, how many people do we need to do this test in to validate it? Because when you're doing a test, you will have to validate the test. So imagine that you are a CRO, you are a contract research organization, and the company, a biotech company, comes to you and say, hey, we have a new test we've created for like a rapid test for XYZ, a rapid test for pregnancy, a rapid test for COVID. And we want to test and validate this this new thing. Like, so please, can you design the study for us? So essentially, what you have to do is determine what number of people do I need to validate this in. That's the first thing, right? So that's what we are talking about here. So here is the case study here. You are designing a study to evaluate the accuracy of a new screening test for a disease. If the prevalence of a disease is 10%, the sensitivity of a test is expected to be 90%, and the specificity is 85%. Calculate the sample size needed to estimate these parameters, the margin of error of 5% and the 95% confidence level. So again, you just have to deliver for this company and then say, okay, here is what we need. So let's do that quickly. When we view the world through the eyes of a test, the whole world is either positive or negative. So even if your results come out as indeterminate, well, you still fall under one category. We just don't know what category you're in, right? So that is very important to understand. This is just a quick crash course on what sensitivity and specificity is. So in this case, this is, we have individuals who have the disease, right? The happy faces mean that they don't have the outcome of interest. Or let's say they depends on whether the outcome is a positive thing or negative thing. Let's say the outcome here in this case is a happy stuff. Maybe you won the lottery, right? Or you have some good genes, Sensitivity is essentially saying what percentage of people with the condition or with the outcome can your test detect? So here we have 1, 2, 3, 4, 5, 6, 7. 7 happy faces. Let's say that our test was able to detect 6 of them, 6 of the 7, right? The sensitivity of our test will be 6/7, right? That would be in this case, sorry, I'm misleading you. Sensitivity here, we're using the red guys. So the red guys are the guys with the unhappy faces. Unhappy faces are the guys with the bad condition. So these guys have, let's say, some terrible disease, right? And there are 1, 2, 3, 4, 5, 6, 7 of them. Our test has found 6 out of the 7. So the sensitivity of our test is 6/7 times 100. So this is 86%. So sensitivity measures how many of the people that have the outcome your test can find. And then specificity is saying of those that do not have the outcome, how many can you find? But specificity is as important as sensitivity too, right? If I imagine I did not have if I did not have cancer and I go and the test cannot tell me that, yes, you don't have cancer, that is very disastrous, right? So it is as important to detect cases as it is to detect non-cases. So that's why we worry a lot also about specificity. So in this case, we have 1, 2, 3, 4, 5, 6, 7 happy faces who don't have the outcome. The test can only identify 4 of them as not having a condition. So that means the specificity of a test is 4/7, which is 57%. So essentially then, right, sample size calculation for the accuracy of a test, one, requires us to know that the world exists in 2 groups, those who have the condition and those who do not have the condition, and then knowing how many people do we need to determine the accuracy for sensitivity, and how many people do we need to determine accuracy for specificity, and then you put the 2 together, and that gives the total sample size you need to validate a diagnostic test. So that's how we do it. So let me show you how you do that on the app. You come to diagnostic accuracy, level of confidence, the prevalence of the outcome. Now, again, if you don't know the prevalence, you can put in 50. Why? Because 50 guarantees you the maximum sample size. So but in this case, we know we're told that the prevalence of the outcome is 10%. 10%, this is the value here. The sensitivity of a test is what was the sensitivity? It's 90%, right? And so you have the values there that tell you what to do. So 90%, the specificity of a test is 85%. The margin of error is 5%. Confidence level is 95%. And the anticipated response rate, again, depends on how many people are going to answer or not answer, right? And so in this case, we need 1,601 people in our study to validate this new test. And again, this is the formula. This is the part of the formula that addresses sample size calculation for the sensitivity. This is the part that assesses sample size calculation for specificity. And you can see the final sample size is simply the sum of the sample size for sensitivity and the sample size for specificity. And those are the parameters there. So any questions? I think that's the end of our lecture. That's all we have. So bottom line, sample size is just an approximation, right? Of course, but you need to use the right formula. You need to be aware of the formulas. It's science, obviously. But this is general how you would follow for the different study designs. Okay.
There's a question.
Any question here?
What do we do for studies when we can't get the prevalence of outcome in control or in intervention arm?
Okay, I think we answered it already. You said we use the population, and if you can't get in that population, look at the next population. After all, we're not that different after all. And if you can't get the next population, look for it elsewhere. If you can't get anywhere, try and be as conservative as possible. It's okay to guess. See how we're guessing 50% when we don't know. But don't guess for a number that will give you, guess for the worst case scenario. If you're going to guess, use worst case scenario guessing. Then that means that you're being conservative. Don't just assume that life will be fair to you and the sky will be blue. No. Assume the worst case scenario and say, okay, since I didn't get the value anywhere, this is my guess. But guess is also robust because we are the worst case scenario. Like I say, aim for the stars. If you miss, you might hit the birds, right? So we've aimed for the worst case scenario so that we know we are covered, regardless of any scenario we find. So that's what you do. Any other questions?
Hello.
Yes.
Yeah. So thank you so much for this. I just have just a small question. regarding the analysis as well as the sample size. You know, some statisticians guide that if you're doing some descriptive analysis, for instance, you're using a t-test or you're using analysis of variance, then there's a particular sample size you can use. But then I feel like this all depends on the study design itself, and also what are the parameters that you are looking at in terms of what's the prevalence in the exposure, what's the prevalence in the control, and also in the placebo. Yeah. So my question is, should we look at the sample size based on the study design, or we should look at the analysis that will be employed? Because some of the analysis, like when you look at the t-test, it's more like just a descriptive analysis, but at the end of the day, you need to do more than a t-test. So should we base our sample size on the inferential statistics, or should we be based on the study design itself? I think that's just one thing that I want to have it clear. Thank you.
Okay, that's a good question, right? So so the point is, this is why you have to plan your studies carefully, right? And this is also one of the reasons why whenever you're doing a study, one of the things you need to have in place is what we call a statistical analysis plan, right? The statistical analysis plan tells us how the data will be analyzed, right? So, you know, if I'm doing a study and I have my aims, you know, aim 1, aim 2, aim 3, it is not enough to write a protocol. The protocol says, yeah, this is how we're going to collect the data. The statistical analysis plan should say, this is how we're going to analyze the data. And for those of you who will ever go into the world of business in research, you have to always write, whenever you write a protocol, you also have to write a statistical analysis plan. In fact, we call it PSAP, protocol and statistical analysis plan. Those two things go hand in hand, right? And the whole idea is that it's to prevent you from cheating. It's not when you collect the data that you now start saying, now this is how we're going to analyze data. No, right from the very start, you're going to analyze, you're going to determine this is what the aims are. This is how we're going to analyze the data. You can even come up with dummy data and say, these are the kind of figures we're going to do. These are the kind of tests we're going to do, right? And so when you now collect the data, everything is done per protocol, right? You're not changing the wheel. You're not moving the goalposts, and all of that. And so that is the appropriate way to do. So that drives the research question drives the methodology, including the statistical test, right? So if I determine that this aim, I want to compare the mean levels of, you know, blood sugar levels among these 3 groups, right? Okay, I know that, okay, this is the sample size I need already. That has already been accounted for in the calculation. So it's not that when I come back later, then I have to start moving the goalposts. In reality, however, most times we just inherit data sets that we had no hand in planning for, right? So in that case, you just deal with what you have. And that's why for almost every statistical test, we have a parametric version and a non-parametric version, right? The parametric version is when you have a large sample size, like 30 or more people, right? Because the magic behind 30 is that when you hit a sample size of 30, right, then you meet the requirements for the central limit theory kicks in. I believe almost all of us should have heard of central limit theorem. The idea behind central limit theorem is that when that assumption kicks in, it doesn't matter the distribution of the population at all, right? You know, we don't care so much about the distribution. So that is why we go ahead and use methods for parametric data. But at a small sample size, you know, you can also use non-parametric methods. So my answer really will be plan your study, design it very well, develop a statistical analysis plan, especially if you're writing a thesis or a dissertation, right? Those are very important. It's just good practice to develop, knowing that, okay, if I'm doing a study, I have to write a plan, include a plan on how I'm going to analyze the data so that I'm not moving the goalposts all the time. So that the sample size I calculated, I know that it will be sufficient for all I want to do. I hope that answers your question. Okay, there's another question there. Is the SAP part of protocol methods? The protocol and, generally the protocol and the SAP are generally different documents. That's what we call it PSAP, protocol and statistical analysis plan. So, but there's no hard and fast rule, right? Some people can, in general, every protocol has a small section where you say analysis. That is not what the analysis plan is in this context. A statistical analysis plan is a much fuller document that talks about in detail how the analysis will be done. So it's not just that small paragraph you have in your protocol that says, oh, we're going to use descriptive analysis for the data and we're going to do regression analysis. It's a much more detailed document than that. So you can put it together, but in general, they're typically different documents. So you have a protocol which tells you how data will be collected, the methods to address issues of bias in the data collection, right? And then the analysis plan, statistical analysis plan, talks about how the data will be analyzed, the data that you collected with your protocol. So they are the two documents, and together they give you a very holistic picture of everything about the study, from the design, implementation, and then the analysis.